Welcome. You're listening to Under the Surface, a podcast where we have in-depth discussions on computer-aided techniques in drug discovery. Welcome to this episode of Under the Surface. I am your host, Chris Williams, and I'm joined today by my co-host, Dave Thompson. Hello, Dave.
Hey, Chris.
Our guest today is Jason Cole, who is currently a senior research fellow at the Cambridge Crystallographic Data Center, also known as CCDC. Jason has decades of experience in modeling and computational chemistry. Thanks for joining us today, Jason.
It's a pleasure to be here. Good to meet you.
Excellent. So there's lots of things that Dave and I want to discuss with you because of your experience in this field. You've got quite a career. But let's start off with your history. Tell us a bit about where you grew up, how you started in chemistry, how did you get interested in scientists? Let's start from the beginning.
Well, it's an interesting story. So I guess many years ago, I used to live in Italy when I was a child. And I think that actually sparked my interest in science was actually living through an earthquake. So there was an enormous, showing my age, there was an enormous earthquake in 1980 in Naples, and essentially seeing a wave coming down your road towards you and the lampposts kind of going back and forth underneath and above that wave, really did spark an interest in science. And in some ways, it's surprising that I didn't end up as a volcanologist or someone going after earthquakes or something like that. Because as a sort of 9-year-old child at the time, it wasn't scary to me. It was just fascinating because I didn't really have a full appreciation of just how dangerous it was. If we're honest, I think I'd react differently now. So that really sparked an interest in science, and which carried on until I kind of got to degree. And as ever, things move and change. I decided to go and do chemistry instead of earthquakes. So I went to Bristol University and did my undergrad there. And while there, I met Professor Judith Howard, who is she's I suppose you say one of the students of Dorothy Hodgkin. So she studied under Dorothy Hodgkin for her PhD, and she encouraged me to kind of get involved in crystallography. So she had a part 2 project in Bristol doing crystallography. So I joined that, and I really enjoyed the part 2 project, and kind of was a bit of a duck to water really with it. Just was clearly something that I quite liked doing. So Judith then, at the end of my degree, announced to me that she was moving university, but she'd like me to come and be one of her first PhD students in Durham, ironically, alongside another student called Nigel Pitchford, who's currently one of the trustees of the CCDC. So it's a very small world. So we both went up to Durham, and I was meant to be building the first molybdenum rotating anode in Europe. I obviously wasn't building it from the metal parts. We were having it delivered. It was being built actually by a company called Siemens at the time, who I think they've been well taken over by others ever since the Siemens arm of crystallography. But this thing arrived, and we were commissioning it, and as a consequence, as we actually got it up to about half power and commissioning, I left it doing some test data collections overnight, came in the next morning, and it had completely flooded the laboratory, because what had happened is the rotating anode had a fault. And the way these things work is they actually spin, and they actually cool. They have lots of water that actually goes around in the top in the anode, and that cools the molybdenum. But unfortunately, obviously a design fault meant it stripped it off. The water comes straight down the column into the generator and completely destroyed the machine. So we were told this was after 9 months of being in Durham, because it had taken that long to arrive. So I was 9 months in my PhD. My PhD was meant to be building this machine, and it's just blown up. as a consequence of that, partly as a consequence of that, we realised that by the time the replacement had come, my PhD would be pretty much finished, and I wouldn't have time to do it. So I had to do a different project, and I'd already got to know Frank Allen from CCDC because he was actually supervising Nigel, the other student who'd come along as well. That was a sponsored PhD with the CCDC. So Frank sort of said, well, I've got a couple of projects you could do instead. So I basically picked that up and got into coding, got into software in a big way at that point, because that was what these projects were. I'd already been doing a bit of coding for the rotating anode machine, but I was writing the software to control it and stuff. So, but anyway, I picked up that. And of course, one thing led to another. I got very interested in the projects which we were doing with Frank, which were to do with symmetry and crystal structures and lots of very interesting areas there. Did that for the rest of my PhD, got my PhD, just not in the area that I originally intended to get it. And then inevitably Frank sort of said, well, and to Nigel as well, so to both of us, why don't you come and work for CCDC? Which we both duly did. Both at the end of our PhDs went and took up jobs at CCDC. Nigel, after 18 months, decided he wanted to go do an MBA and become a hedge fund, or not hedge fund, become an investment banker essentially. So he disappeared off to do that, but I carried on. And at that point, I was involved in the software that we use for creating the database here. Very ancient software now, but then another project came along because one of my co-workers, in fact, the sort of second in command at CCDC, a chap called Robin Taylor, he said, "Oh, we've got this opportunity to take on this piece of software called Gold." And he said, "Do you think we should do it?" And there's a funny story with that as well, actually, that software, because it was originally offered to Tripos back in the day, and they decided they decided they didn't want to pick it up, so they decided they didn't want to commercialize it. So
where did Gold come from?
Gold came originally from Sheffield University with Pete Willett's lab, and an absolute genius, a genius of a chap called Gareth Jones, who's a really, really. My one regret is that we don't have mountains actually in here in Cambridge, because I would have loved it if we could have got Gareth to come work for us, but it was just so flat. There was no way he was ever going to work here, and so he disappeared off to go and work in the Rockies, the Rocky Mountains for somebody, because he just loved climbing so much. But so we never managed to keep him, which is a real shame. But anyway, because we couldn't keep Gareth, I was asked to take the project on and turn it from academic code into something that could be commercialized. So I duly did that, and of course, Gold was a huge success.
So I want to stop there a second, Jason, because we've bled over into the CCDC years, right? So you left your PhD and you went to your job, and you've had this job since you left your PhD.
I have indeed. I've been in CCDC ever since and done various different jobs all the way.
Chris, does that give you a run for your money?
I think it does, because actually I finished my PhD and then I worked at a college for about a year. Then I started at CCG, where I've been since 1998. So I started at CCG, consulting in 1994, but officially in 1998. So when did you start at CCDC?
So I started at CCDC in I've got to think about that now. It was 30 years ago. This February just gone.
Oh, so 1995.
Yeah, so 1995. So I started there. As I say, I started as a junior software developer, and eventually ended up productizing Gold and doing all of that, and then slowly.
Well, let's talk a little bit about CCDC, because I think some people know about it, some people don't, and I think you've been there since the beginning, doing all these different software. So we'll start there, and then we can talk about the different products you've worked on and things like that, right?
Yep, absolutely fine. Okay, so for the people who don't know, I could probably tell you a little bit about what CCDC is. Mm-hmm. So CCDC, or the Cambridge Crystallographic Data Center, is an organization. It's been around for 60 years this year. So we've been around for quite a long time, and the primary function, and indeed our charitable remit, because we're a registered charity and a not-for-profit organisation, but our primary function is to collate and disseminate crystallographic information. So our original founder, who's Olga Kennard, was quite visionary, really, in that she saw that there was going to be data, lots of structural data coming along. And originally they decided that they wanted to collect that structural data back in the 60s when there were tens to hundreds of crystal structures in the world. And of course, each one was a magnificent investment of time. So what happened was Olga and others, they set up 3 different institutions that, in fact, ended up, I think, 4 in the end. But initially, I think it was 3 institutions: the Inorganic Crystal Structure Database, the R database, which is organic and organometallic small molecules, and then, of course, that small pretender, the PDB, all those 3 databases. I think the PDB came after the CCDC. So the Cambridge Structural Database was first, and then when proteins started to be crystallized and structures of proteins being done, then Olga actually aided the setting up of that at the time. So originally we were very, very aligned with the PDB in a sense. Even the original PDB data format, you may not know this, but it's actually a CSD format. It started out as the CSD way of representing crystal structures, and then was taken and adapted. So at the end of the day, don't blame the PDB, blame us.
I was just looking at some PDB file parsing the other day, the 80 characters and
Absolutely. Different times, of course, because I think I deal with young software developers from time to time, and they often will look at things and say, "Why is it like this? Why is it like that? Why is it?" And the reason is they don't understand that there were very, very different drivers when you didn't have gigabytes of space, or masses of memory, or all the things that everyone has these days, and so they see things and they don't realize that they're put that way for very much driven by efficiency. And,
I think that's such an interesting and important point, right? So you have a young software developer looks at a piece of software and like, who's the idiot that wrote this? And then, but that's the sort of natural reaction, right? Jason raises his hand. It's like, actually with me. No, but that seems to be the natural reaction, but they should be so lucky to have made decisions based on the design constraints that you'd still be considering 30 years in the future, right? Like,
indeed,
that is like just, maintainable software over that time frame means something completely different, doesn't it?
It does. I mean, very, very much so. And also, I think one of the things I learned fairly early on in my career, which was taught to me by another very good software developer we had at CCDC, who's retired now, but Claire McRae, and she taught me something that she'd learned from somebody in Microsoft at some point, and I can't remember who it was, about don't throw code away and rewrite it. If a software developer comes to you and says, we need to just totally rewrite this, usually that's the wrong answer. And the reason it's the wrong answer is because you've invested years and years and years of effort and energy into a piece of software, and you've debugged it, and you've kind of, you've ironed out loads of corners and edge cases that maybe you wouldn't consider. And if you rewrite it, you just put them all back in again. So if you're going to do it, you've got to have a really, really, really strong and good reason to rewrite a large body of code. And it does happen from time to time, but it's a bit like in cricket. The very famous, I think W.G. Grace once said, if you win the toss, you bat. If it's a green, awful pitch and all of these sort of things, you think about it and then you bat. There's no. You don't ever do the other option, and it's another one of those sort of things that I think that people need to really be mindful of total rewrites and the like.
Oh, yeah, definitely the edge cases, and even when I go through my own code, it's like, who wrote this? What idiot wrote this? And then I did 5 years ago, right? And I'm looking at, what the hell am I doing here? What the hell am I doing here? and then I comment, and then something breaks. Oh yes, I forgot that when these things are in a line, the cosine, and so you're right. Someone said, coding is 10% coding, 90% debugging. Because you've got the idea, and then you go through and you test it, and you find the edge cases. You find these little things you didn't think of in the original design. Which, to your point, if you're doing a rewrite, well, this code does this, but it's got all this stuff in it. Let's rewrite it. Well, it's got all this stuff in it because when they did this a while ago, they did it and they realized all these issues, and they put all that stuff in, and it's very easy to think it's kind of meaningless and gloss over it and then make the same mistakes again.
Indeed.
Jason, do you know much about the backstory of how gold came to CCDC's attention? Like, do you know if the CCDC were looking for a thing, or?
In a way, I don't think we were. As I say, the story where it goes, what happened was it was developed originally in Sheffield University in Pete Willett's group, and they'd already developed a thing called GASP. So, which is essentially it's a ligand overlay program that uses a genetic algorithm. Sounds pretty familiar, doesn't it? And so that Gareth had written that as well, and that had been taken on by Tripos into the Tripos environment. But for whatever reason, Tripos decided not to pick up gold, the ligand docking program. And so Pete was looking for an organization to commercialize it. Pete Willett was looking for that. And because of relationships, as ever with these things, he knew Frank and he knew Robin. They sort of said, well, what do you think? Should we do it? And Robin, primarily, I think, but convinced Frank, and eventually convinced Olga, and that was quite a challenge because Olga was not actually that keen on the idea at the time. Again, she felt it was kind of a divergence from the core of what we do. But convinced him that it was worth taking on. And I think it, again, a really interesting education. What was the principal success point, and the thing that really made it a success is another interesting thing that people might hear. And for future software developers, this might be a useful thing. You're developing a new area or a new thing. What probably really sold it to the community was that Gareth and Robin, the first thing they did was to develop a really quite significant test set. So they built about 100, this just seems tiny now, but at the time it was huge. They built a set of 136 protein ligand crystal structures, so proteins were ligands bound, and then tested it on all of those. They tested on 100, and then they left out 36 and tested it on those after that, as a genuine test set rather than a tweaked training set, and showed that it got a success rate of reproducing the pose within a certain threshold of around 70%. And so they were able to publish that. And just published a paper saying, this is how this performs. We got this number of structures. This is how it performs on those. There you are, carry on. And that was completely different to what anyone else in the field had done, surprisingly. So surprisingly, what tended to happen with docking programs is people would get 2 or 3 structures, and they'd show that they could maybe reproduce the pose for those couple of structures. And suddenly the entire field's been told, well, no, you've actually got to validate it properly now. Against a much larger test set, and as a consequence of, that's probably controversial, but it's a sort of step change. You see it in other fields too. I run into, for example, software recently for doing predictions of morphologies, and I've not seen any papers that actually validate those morphology predictions on large numbers of structures. They tend to again, it's 2 or 3 here and 2 or 3 there. And I do think it's a sort of step change. When you have that sort of step change in validation, it sets a bar for everybody. And we still find, even now, that when papers come out on new docking algorithms, very often they still use the same test set or they still validate against those test sets that were generated over the time. And so it's, so I think that is an interesting lesson for if you're developing a new method or something on those. Get a good validation set, demonstrate how your software will perform on that. Not only because if it doesn't work, you learn something as well. I mean, that's the really important thing. Yeah. And it's a sort of defendable position as well.
Yeah. And actually the putting together that data set, it's not sexy. Right, like everyone wants to develop algorithms and new things, but from docking especially, the dockings had different resurgences of validation, passes. There was one time, I think in 2008, when the ACS had 2 or 3 sessions on docking validation. All the dockers were, being compared, et cetera, and there was different data sets coming up. But one of the problems that came up was the data set preparation. You've got a PDB structure. Well, it's missing some atoms. It's missing some hydrogens. Where do you put them? Right. And that can affect your docking results. If you prepare the structure this way and you flip the ambiguous residue that way, you get the wrong pose. But if you flip it this way, you get the right pose. And
And latterly, of course, there's no guarantee that the experimental results are perfect. There's a lovely paper by John Liebschutz, relatively recent, a few years ago now, where he had an original paper called The Good, the Bad, and the Twisted, which is about strain in PDB structures. And that was a reaction to a description of I can't remember the author now, but there were papers where there were claims that structures, the ligands could have more than 25 kcal.
Oh yes, I know what you're talking about. There was
I think it was the Sitzman papers. Was it Sitzman?
I remember Parola as a name coming up. Anyway, we don't have to name names. Right?
No, indeed. Wind that back. Yeah, no, indeed. Yeah. But it said, and which was, to us was very, very surprising. And I know to John it was. And it led him to then try to look at strain within PDB structures in general. And then, but the follow up to that, which is in some ways I found even more interesting, is he looked at high resolution crystal structures in the PDB, really high resolution, which now we're getting more and more of these, and found that actually quite often the ligand pose is disordered. And the working hypothesis is that a lot of those older structures might actually just be the averages of multiple different binding poses. And in the new structures,
hang on a second, Jason. Are you saying that these systems are in motion?
I think disorder doesn't necessarily mean in motion, but I think they are
perhaps dynamical then. They're not static.
Well, they could be. I think protein structures are in motion, right? Of course they are. They're wiggling around. But as a crystallographer, we'd always say we can't tell whether it's dynamic motion or configurational. So, in the case of a disordering of a ligand, it might not be in motion, but it might actually be that there are multiple different ways round that ligand can fit into the binding.
Oh yeah. So instead of just jiggling, what happens is it poses.
So some of the active sites have got it in one way, some of them have got it in the other way. And so, but you can't, as a crystallographer, you can't easily resolve the difference between those two situations.
My facetiousness was punched in the face by your exactitude, and I appreciate it.
But proteins do move, absolutely. Yeah. I mean, clearly they do. I mean, side chains move, and what Chris was saying earlier about curation of data sets up front, I think is really, really fundamental and actually really quite hard. And to get it exactly right is very, very challenging.
Yeah, I've always said it's kind of like it's the work that you want to give to an intern, but only a person with 30 years experience can do it.
Yeah. Well, yeah. I think Yeah, I mean, we spent quite a lot of time. Definitely, I remember the original validation set. I think was done by Gareth Jones, who wasn't. I think his first kind of degree was more in informatics and informatics and that side of things, and coding and software, rather than full on biochemistry. And so I think it took him and Robin about 6 months to pull that test set together and do all of the curation work. And Robin, the super clever man, and really fiercely knowledgeable about the chemistry, and still had to. He was faced with that challenge. So. But at the end of the day, it pays back. It's a worthwhile investment. Let's put it that way.
Yeah.
Yeah.
Had you any experience? Sorry, Chris. Before we moved on from gold, I got two questions. One of them's super silly, but I always make a joke about it. And the other one is, before any experience with gold, had you used any Dockers before? Like, what do you think of this whole docking business?
I hadn't. No, I was completely new to it. When I came into gold, I came in as a software developer with a job to commercialize something, and therefore, the first thing I was interested in wasn't so much the algorithms that it was using in detail. It was more, well, does it crash? And why does it crash in this particular case? And stuff like, and tedious things like, is it easy to use? And, is the language that it's using behind the scenes easy to grasp? And do we have a reasonable GUI for it? And all of those sort of things. But then latterly, with gold, so the later versions actually do have some of my science in them. So if you've used constraints in gold, some of them will have been written by me. If you've used waters in docking in gold, that was mainly written by Aztecs, by Marcel Verdonken and his team at Aztecs. But I collaborating on that. So we work with, heavy collaboration there. Scoring functions, if you've used different scoring functions in gold, I've had my hands in there as well. So we wrote ChemPLP. Well, a chap called Oliver Korb wrote it, again, supervised by me. And so, although Ollie came from a different docking program originally, came to CCDC for quite a long time. So it's so the sciencey bits. And a really lovely experience. Again, talking about sort of experiences in your life. Many years ago, I was at the European Crystallographic, not the ECM, Euro QSAR. That's right, the European QSAR meeting, and a speaker got up on stage, and a couple of years before I'd written constraints to do a particular thing that allowed you to tinker the dockings and make sure they fill pockets or do various different things in the ways that you wanted to do. And the speaker got up and they were talking about a drug program where they got it all the way to phase 3. And I can't remember the drug now, but it is now, out there and, in patients. And they were talking about the virtual screening and the screening processes where they'd use a docking program. And they said, and he got up and he said, we use gold. And the reason we use gold is because we were able to constrain the poses in exactly the way that we wanted to fit with our prior hypothesis. We know that this fragment is going to dock into this pocket, and so we made a protocol that allowed us to do exactly that. And he said so, and that really accelerated the project. And I sat there thinking, I wrote that.
There you go. Well,
that's a lovely feeling.
Because it gives you a feeling that your life's work isn't meaningless. Like you actually,
indeed.
Well, we all want to feel appreciated, right? And I think like it's almost like being an artist, I guess. You can make a painting and you like it and it works really well, or it's pretty. But if other people say, yeah, I like that painting, it's my screensaver, it gives you a validation the same way that, and that's, to me, that's the kind of validation I like the best about my software. Because we do talk about validation studies, and I've got a bit of a mixed feeling when people use the term "my software is validated," right? Because it sort of stops people thinking about testing it yet again, right? Like it's good to validate it and show that it works on a certain data set. But if it works well on a data set, doesn't mean it's necessarily going to work on other data sets, right? So sometimes validation becomes like software's validated, scientist turns off brain, and accepts the plus, and especially with docking. I want to go back to those constraints you were talking about in Gold, because I've never used them.
All right.
But what you're saying is that, if I want to dock something, complete physics-based docking will just try and, put things everywhere and things land where they may based on the physics of the system. But from what I'm understanding here is you're saying, yes, do that, but you also want to make sure that these certain interactions are maintained and other. So it sounds to me a lot like a pharmacophore.
Yeah, sometimes. I mean, effectively, it is a similar sort of thing, right? That quite often people will have knowledge prior to kind of using a docking algorithm. A docking algorithm will shovel the molecule in some way. It will do that, and it'll find a way of doing it. It doesn't necessarily mean that it's a good scoring kind of pose, but you can have a situation where people will know that this pocket is always occupied by a particular fragment in their series, and they just want poses which actually represent that pharmacophore. They don't want poses that represent a different possibility. Yeah. The physics-based, if I'm brutally honest, the scoring functions, they're okay, but they're still not brilliant. And so, any additional information that the user puts into the process is usually beneficial if said information is true. Normally it is. People do.
Well, and maybe back to your point, where if the ligand actually has two different binding modes, and we're sort of getting some sort of average, that pharmacophore that we're creating for the crystal structure may be some sort of blurred thing between the two actual ones. Right.
Yeah. I guess it doesn't have to actually be true. We just have to believe strongly enough that it's true enough for the data we have at the moment.
Yeah. And I mean, it's also why I think in software I encourage. I like people making use of our data, but any data in these things. So behind the scenes in Gold, it uses torsion patterns, for example, to limit and constrain what conformations you see. Scoring functions, we have one that's called ASP, which is essentially is a statistical potential built on observations. Actually, in that case, let's we've talked about Gold, and you alluded to this torsion profiling thing, which is another product that we integrate with. So we do want to cover integration. Right, because we software integration. So CCD integrates with Mo and some other software too, and Gold being a docking platform that it's very popular. But also you have a product called Mogul, which I think that's correct. Yeah,
which I don't think people are as familiar with, but I think it is along the lines of what we're discussing, because we talked about strain before. And the strain energies in a lot of PDB structures at first glance are quite high, unrealistically. So ligand strain is another issue in our field, right? That it's maybe not dealt with. And I think Mogul has sort of one way to stab at this with these torsions. So maybe you can tell us a little bit about what Mogul is, what it does.
I can tell you a little bit about that. And Mogul stands for, I can't remember now. It's a molecular geometry library with a U. I'm not sure. We kind of shoehorned the U in because we could get the word Mogul, I guess. Yeah. And maybe somebody liked skiing or at the time. But anyway, Mogul, it's a library of molecular geometry, and it's not just torsions. Actually, it's rings as well, and it's got bond lengths and bond angles. And actually, the bond lengths and bond angle data is probably as important in hard card carrying crystallographers are interested in that sort of thing. So it's not just about torsions, but in the context of drug discovery, what we find people will do is they will go and look up in that library, the closely related structures in the CSD, which is essentially what it's doing, and extract the distribution of observed torsion angles that have that similar chemistry. And the way Mogul works is essentially by a dynamic keying approach. Ironically, it's one of the few pieces of software at CCDC where, while I have had some involvement in, most of it was written by other people. So in the case of Mogul, I wrote the very original prototype that we had for Mogul. It took me literally about a month to write a little piece of software that was a very, very crude text file and file descriptors and stuff like that, and essentially a glorified key. You can these days I wouldn't even contemplate doing it that way. I'd start with something like a hierarchical smarts pattern or something like that. But at the time that was still very nascent and not really a thing. And so yeah, essentially we came up with this sort of keying mechanism where you have keyed substructures essentially that are hierarchical, and the things on the peripheral of the key are lower down in the chain, as it were, and can easily be generalized. So you can work your way up a kind of generalizable key, if you like. And that's the way that Mogul works. It has all the CSD keyed and indexed based on that type of information. And what happens is you draw back then, I say, distributions from the CSD of compounds which are of a similar nature to the one that you're interested in, and you look at the pattern, how the torsion angle behaves in that thing. And a very common use case, and particularly I think in the MOE use case, is people will be looking at a structure and they'll just say, what's usual, what's unusual, what is it I need to worry about in the context of this structure? And sometimes you'll get back results and you'll think, oh, that looks unusual, but it's not necessarily that the experimental information is wrong. It might actually just be there's a reason for it. One of my favorite examples, because we don't just use Mogul in Mogul, the Mogul data, we also use it inside we use it in gold, but in a sort of flat file there, because we want the data to be very, very fast to access and very, very lightweight. So that's a little design decision, but also we use it in our conformer generator. We use actually rotamer libraries rather than torsion libraries there. And what you can do there is actually do direct conformer generation from those particular patterns. So it's a very, very diverse and useful kind of source of data for lots of different things. And as I say, you can use it for this sort of validation type piece where you go in and you look at whether you got user or unusual features. I got onto that because the conformer generator, which we use in the paper that we wrote on that, we did significant validation. I talked about validation before, and one of the examples that I found where we didn't generate the structure, the conformer that is observed in the PDB of a structure, and it turns out even in that molecule, even bond lengths and angles in the compound looked a bit unusual and strange. And it's one of my favorite examples because it's an example where the PDB structure is not wrong. It's a quite high resolution structure. It's quite a good structure. But when you really dig deep into the paper about it, the structure is a snapshotted thing that they did at one of these free electron laser type experiments where they managed to capture this structure just at the transition point of doing the chemistry that the enzyme does.
Oh, okay.
So, of course, the molecule is in this really distorted state for a really good reason. It's like that. And you wouldn't expect to see ground state crystal structures having bond lengths and angles and torsions that are like that. It's just because the chemistry is going on. This thing is about to fall apart, and they've managed to snapshot and freeze it at exactly that point in the structure. That I think was probably in that one of my favorite examples that shows that unusual means unusual. It doesn't necessarily mean wrong. Sometimes it does. Sometimes, but it means be cautious. Think about this. That's really
it depends, right?
Yeah. It's
so you built the initial prototype for Mogul. Was this a thing that you were asked to do? Was this an opportunity you saw and thought, oh, this might be a fun little product?
It definitely was a thing that I was asked to do by Frank and Robin. Likewise, I work with a chap called Scott Rowland, who's you may or may not know. But Scott and I worked on a product before that called Isostar, which was the first thing we did, and we wrote that together.
So actually, I'll interrupt you for a second, Jason.
Yeah.
Scott Rowland was a previous guest on one of our podcasts.
Well, Scott's an old friend.
Yeah. So, I think we've talked about Isostar with him. So tell us about Isostar.
Well, okay. So Isostar is essentially a library of interaction data. So what you do is you take substructures in the CSD and substructures in the two pairs of substructures, which you hypothesize might interact with each other, and you construct a query under the hood, which queries the CSD and says, find me all of the instances where this fragment is interacting with this fragment. At the simplest level, that's what it does. Go away, draw them all back, get all those hits back, and then build a kind of a 3D cloud of one fragment around the superimposed other fragment, right? Mm-hmm. And that's what Isostar gives you. It's a library of around 12,000 interaction plots that kind of combine those things. And that's really nice because we can take that information and we can do things like combine those plots to make maps of binding sites. For example, you just superimpose on protein groups and see where the interactions are in that, and so on and so forth. And it's been applied there. We apply it to crystal surfaces. We apply it to all over the place. So it's a library of interactions. It's nice and three-dimensional and quite easy to interpret. Some interesting science in it. The real challenge, and I still think a challenge which we often face, and I've done other work with Bernd Kuhn and Andy Tostorff and Robin as an emeritus fellow, looking at this again more recently, but looking at how you properly scale the frequencies of interactions within database searches is quite a challenging thing. It's not as trivial as you might think, and many people have done work in that space. Most recently, I say Robin did this RF type measure where he looks at the relative frequencies of particular fragments and tries to put it on a sound footing. But you see papers where people will find in the CSD two groups, functional groups quite close together, and they'll conclude from that those two things must be interacting. But that doesn't work unless you consider the number of times they don't interact. It's how you generate those sort of scaling factors is actually quite interesting. And Isostar has a way to do it.
So is that because the data is kind of biased? I got lots of crystal structures with that type of interaction because they're easy to make, but really I should have other crystal structures.
I think it's more. I think the most common thing is not so much make, but more those functional groups just are very, very frequent. For example, if you think about a fluorine atom, say an aromatic fluorine, you'll see interactions, hydrogen bonds occasionally to aromatic fluorines within the CSD. But then when you look at the structure, it's actually pentafluoro. It's got a pentafluoro group on it. So there's 5 fluorines in that structure. Yeah. And there's not a lot else. So what is it that a crystal structure is going to do? The fact it crystallizes, I suppose, tells you that they must want to be, there can't be massive unfavorability of interactions. Although you do occasionally see that too, where there'll be a secondary contact within a crystal structure, which is not particularly attractive, but other interactions are, causing that to happen. And so the drivers aren't necessarily that. The drivers are something else in the crystalline lattice. So you do see, so scaling things like that and factoring things like that into any method is actually quite challenging.
Yeah.
These sort of secondary interactions and where whether something's happening for other reasons other than what you would naturally interpret them to be. My favorite one, again, fluorines. We did a paper with Robin on specifically on fluorine, and we were looking at fluorine hydrogen bonds, which do occur, but they are very weak. And when you actually look at them, usually the hydrogen bonding group, the hydroxyl, is actually bifurcating the fluorine and something else. Mm-hmm. So it just happens that motif is, can lock in, and it forms a nice hydrogen bond here. And that this FH contact over here, it's not particularly repulsive, so it's fine. Mm. So understanding those sort of things, I think, is an interesting challenge. You do see differences. Bernd and Andy and we did see differences in frequencies sometimes in the PDB of weaker interactions as compared in the CSD, which I found initially surprising, but I thought about it and it actually does make sense. It's because most protein structures are crystallized from water. In fact, I'm not particularly aware of any that hasn't been crystallized from water. I think, that is the solvent that you have to use. Whereas, of course, small molecule structures are crystallized from all sorts of different things. Yeah. And so if you crystallize something from, I don't know, say, trichloromethane or something like that, then you're going to see different patterns and different solvation drivers going on, and so drivers as to what crystal is going to be formed.
Yeah, I mean, waters are integral to a lot of the interactions between ligands and proteins, and they're as part of the cloud, right? So if you were to take the waters away, maybe there would be different interactions, right?
Different desolvation effects, different drivers. So it's a hard problem. I think that's why scoring functions are so challenging. Is because it's almost impossible to easily model in a very fast way the sort of desolvation effects and pre-organization effects that can happen, for ligands and so on and so forth. So
I always appreciated the simplicity of the original doc scoring function, which was just a Coulombic term and a Van der Waals term, and then you could add on whatever you wanted after that, right? To your point about constraints and pharmacophores and things like that.
But
I was curious. So Mo plays nicely with Mogul, and Mo plays nicely with Gold. To what extent do you think that vendors' software should play nicely with other vendors' software?
I work for a charity, so who have benefited enormously at the end of the day from standardizations of things. So I'll talk about that in a minute. But I understand that there are commercial drivers sometimes. The commercial driver of lock-in and what people would describe as that and that. But personally, I think software we really should endeavor to make things play nicely with each other. And I appreciate that. As I say, that might be seen as counterproductive in certain hyper-competitive fields. Very hyper-competitive fields, crystal structure prediction, right? It's that's an example of one. But we are at the moment working with vendors and with academics to try and develop standards at this point for the data formats of those things. And I think I'm not doing that. That's being done, led by Ian Bruno and Lily Hunniset and Isaac here at CCDC, alongside lots of academics and other parties out there in the wide world, which is a sort of follow on from a thing that CCDC does called the crystal structure prediction blind test, which may interest you. But anyway, they essentially were trying at this particular point to come up with a data standard. And the reason for that is because CIF, it was just transformational for CCDC because it makes it very easy for us to aggregate the information that we want, and it means it makes software much more interoperable. All the software vendors who want to do crystallography have written a CIF format reader, right? Why have they done that? Someone had to come up with that format. And indeed that happened, 15, 20 years ago now. And that, I think, and actually it makes people's lives just that bit easier. So I think, standard, like an example, I think where software vendors probably really should standardize now, smarts patterns. So we've all got our own subtle little nuances in our smarts patterns, haven't we? That work slightly differently. Well, what does D mean in your smarts pattern? What does X mean? Does it mean exactly the same? When you talk about number of rings, which number of rings do you mean? And it's just all those sort of little tiny subtleties. And actually,
I think didn't Inchy try and do that?
Inchy is still trying, but Inchy is not like smarts and not substructures.
It's just the smiles, right? Yeah.
I mean, Inchy is a molecular identifier rather than a substructure identifier. But even so, indeed, Inchy did try and is still doing that. I mean, there is still a big effort to try and get Inchy's. I mean, from a data side of our organization, we're really interested in Inchy's, and that to us, they're really important because they're opportunities for us to sort of do cross-linking of data in ways that we could have never done in the past, because the difficulty is chemistry is an absolute, bit of a git, really, and there are.
That's it. That's exactly the
so many things.
Exactly the rub. We don't know, right? And if you don't know, how can you properly represent? And then if you've decided how to represent something, how do you convince everyone else that that's the right thing to represent? And everyone else is like, well, actually, no, this is what D means in my context.
But that's the big thing with Inchy, though. With Inchy, it's not just a standard; it's also some software. So the point is that if you're going to use an Inchy, use this software to generate the Inchy, and actually then you're using the stand. You're using the same standard. That's kind of the idea. No one's. Whereas with smarts, everyone has their own implementation of these things, and so as a consequence, they're all just slightly and subtly different. And that actually, that doesn't help some poor chem informatician who's working at, I don't know, wherever some Abbott Laboratories or wherever it would be, that's trying to marry up one particular piece of software with another. It doesn't actually help them.
No, we've been through that experience of translating smarts patterns from one system to another, and So I'm all in favor of that from a charitable point of view, in the sense of, and that's perhaps how CCDC differs in some ways to more traditional software vendors, is that we do have a charitable part to our remit, and those sort of standardization of information, those sort of things really do fall within that radar, because it fits to what our charitable purpose is, which is to try and maximize the use of the data that we aggregate and make sure it's maximally used in a sort of so-called fair way. And I think that CCDC, given that we're not funded by grants generally for core operations, we have a few grants for research projects and things like that, but we don't, generally speaking, have large scale grants for academic grants to actually fund the job that the editorial team does. It's actually quite remarkable that the business model has sustained itself for 60 years. So maybe we can fill in the listeners about that. So CCDC is a charitable organization, which is different from anything else in our field. We're mostly commercial software companies, either publicly traded or privately owned. But we go and buy gold, we go and buy Mogul.
Absolutely.
In product review. So how does that work?
Well, essentially, the way we operate is we provide our software and services, and most importantly, data. Every crystal structure in the CSD is accessible by anyone in the world basically just you go to our website, and if you know what you're looking for, so if you've got a paper that has the accession codes and the codes says this is in the CSD, you can go to our website and get that crystal structure. Okay, you don't have to pay anything for that. That's the charitable remit of what we're doing, right? And if you know, say you could, if you can search a basic level at that level and get back those sort of information sets and data sets. That's the sort of primary core of what CCDC does. The way we fund that and those operations is essentially by selling advanced access to search, for example, and selling gold, and so and selling software tools in a wide variety of different areas. It also funds other things like so we funded ourselves. We didn't get a grant to do this. The recent crystal structure prediction blind test. So we've been running blind tests for that technology for 25 years now, I think it is, and each test has got sequentially more complex. But to do that's actually quite an endeavor. That takes, a good couple of people for a couple of years working to actually, in fact, probably even more than that, three, 4 people for a couple of years to do it really properly if you want to do that. And that again is the sort of thing that's funded by the funding model of selling software, so access to data and the like, allows us to provide that charitable side. And it also allows us to do things like that. And it allows us to do things like fund efforts on data standards and so on and so forth. So
I think I was initially a little confused as to how it would work, right? Because it seems like there's lots of competing tensions. You make a product, you present the product to the marketplace consumes it or not, and this gets funneled back. But the way you just described it, it's actually very elegant in the sense that everything funnels up towards your North Star, which is just making this material available to everyone in the world.
At the end of the day, that's what when you go to Charities Commission, you look at what CCDC's purpose is. That's our purpose.
Yeah, exactly. And then everything, and then you make money, and then that just gets funneled back in. But that's software maintenance, software development, the blind, the blind prediction tests, the data standards. It's not like we made a bunch of money and now Jason goes to work in a helicopter, right? So,
no, absolutely, definitely not. Yeah. But,
that's very cool. Are there any other vendors in our space anywhere in the world that have?
Well, there are other organisations that. I mean, LASA is one. So the toxicologists. So they're another not-for-profit organisation that was spun out of the university. And again, they're a not-for-profit rather than being a for-profit organisation. I suppose. There are grant-funded endeavours. The PDB would be an obvious one. And the EBI, PDB, and all there. But those are more academic in the sense that they really are grant-funded.
That's what's unique about CCDC. You guys produce a product,
but the LASA is another one. They produce Derek and a product, but they're not for profit. So they reinvest anything any surplus they make in developing new toxicology models and that side of things. So that's probably the closest one that comes to my mind. But there are others. I'm sure there are others that I've probably terribly forgotten. But anyway.
No, I mean, they are pretty rare in our field. Actually, and CCDC, from what I understand, how big is the company? It's about 100 people?
We're about, I suppose, about 90, I think, rather than 100. But we started out, when I first joined CCDC, we had about 30 employees. So we've grown slowly over the 30 years to the current size of around that. We have people, not just in the UK. We have a small team out in the US, Carmen and the team, as you'll know.
Yeah, we've met
Yinka and co. And we have a small presence as well in Asia, and we have partnerships with a couple of an organization in China, an organization in Japan, an organization called Jaishi. Historically, we've worked with them. And we also have software development partnerships all over the place. So we've got a team in Africa, would you believe, who writes some of the stuff that we do.
Where in Africa, if you don't mind me asking?
Gosh, now I think they're in Botswana, but don't quote me on that. I can't remember. But
we've literally just recorded you on saying that. If that's a problem, you should let us know.
I think that you've called me cold. I think they're in Botswana. They might be, either that or Ghana. It's Ghana or Botswana, I think. Yeah. But we have a team out there who it's not CCDC out there. It's actually an organisation that provides software development, but we're working with them, doing some software development, and we also have a link to a place in India too. So for software development too, I'm sure lots of companies do that these days.
And when you think back on the starting 30 years ago, do you ever think you'd be part of a global footprint?
No, I don't think I did. I guess I joined CCDC because I liked crystallographic data, and I was interested in it. And so the driver to me was always science, and still is. There's a reason that I stepped back from being the deputy director of the organisation and went back into science, is because science really drives me, and I really enjoy doing that sort of stuff. I enjoyed writing software too, but it's more writing software to do science rather than say writing software to do, I don't know, licensing or something like that.
Yeah, exactly. You're writing software to basically answer a scientific question that's burning in your brain.
That's right.
And that's actually some of the funnest times I've had in my career has been doing those things, and having other people use that software and find it useful is the icing on the cake.
Yeah, I'm rubbish at GUIs, if I'm honest. It's my weakest point.
I don't like GUIs either.
Yeah, but that's another really important thing, I think, which is that good. So we talked about integrations earlier. Good integrations of software is really important. I also think it's really important to have stuff that's up to date and maintained. So we talked about Mogul earlier. One of the nice things about Mogul is, of course, we can constantly update it with new data. So when Mogul was first written, there were about 50,000 structures in CSD. There's now 1.25 million. So the volume of data in the library has increased massively, and you're constantly getting new chemistries that come into the CSD. That's a fun thing to do, is actually look in the CSD at changes in chemistry over time, and you can see what becomes fashionable. You can see when ferrocene suddenly came in.
Are people banging down the door to get access to this data in a way that informs, we haven't talked about machine learning and artificial intelligence and all that nonsense, but Chris and I are obliged to do this on every podcast. Are people saying, "Oh, you have all the ground truth"? How do we get to that? And how
there are organisations that are keen to use the data in a way, in AI models, and indeed we see many publications where more and more publications coming out where people are doing that. We have to have certain rules, and I think that's really important that people understand those rules. Which is, you can't just take all the data and just basically republish it somewhere else. That's we can't let people do that. And actually, it's not just for a point of view of protecting our business model. That's an important thing. It's also actually because it's detrimental to the community. So if you think about one benefit of a database with the data in it is we can evolve it and improve it over time. Every year we will do our editorial team will have projects where they go back and enhance, improve, and amend the data. So, for example, just recently in the last few months, it's taken us a long time to get here, but because we've been reworking the underlying data formats that we've used, there's been a couple of opportunities to go back and take data from the old archives that we have in-house and make it more available to people. And in particular, in the area of disorder, I talked about crystallographic disorder.
Yeah.
So the representation in the CSD of crystallographic disorder historically has been quite crude. Essentially, we've given you the major version and then suppressed everything else, right? That's how it's been presented. Now we've got an opportunity to go back, because now our new formats can cope much better with it. We can go back and actually repopulate and reinterpret all of that data and present it in a much more cleaned up fashion to the end user. So it's actually more compute ready, and much better for individuals to sort of interact with. And if people take a snapshot in the sand of the data and just dump it out somewhere, you're actually doing a disservice to the world.
Oh yeah, okay, you're right. I get the point, in the sense that not only are you republishing the data in two places, but now they've frozen in time a non-standard, or the not the best form of that data. Yeah, exactly
that, and then they're missing out on the future improvements that might come along. They're also missing out on future larger sets. Now, so we kind of discourage that, and what we encourage people to do is provide the tools that they use to generate their data set. And if they do that, that's a much, much better thing from a sustainability point of view, because it allows people to recreate in the future a new version of the data set that they want in their validation, and maybe get more information that they didn't have before. So that's kind of how we encourage people to either, if they want to use a lot of data, to publish a list of ref codes or a list of entry identifiers, something along those lines, or better still, publish the mechanism by which they actually generated the test and make it easy. In fact, literally 2 days ago, I pushed to our open source repository a brand new, well, actually quite old, but because I used it maybe 7 or 8 years ago, but I finally published it. A way of generating test sets from the CSD. So all you have to retain is a single text file that describes how to do it.
Yeah, I love that.
And you run that script and it will just regenerate the test set, right? So that's the sort of, I think, how we would encourage people to think about data sets, going forward. People do use these things to say they'll take them and there's some of the metal organic framework data sets people have used, and in cases where it makes sense to, we'll have relationships with people to allow them to do that. But we'll have to have that relationship in place to really make it something that's viable and sustainable, really. However, I don't decide those things anymore. That's for the bigwigs, right? That's for the trustees and the executive to decide.
You're thinking about it, so that's good. I got one flippant question, right? I had actually 2 questions about gold. My flippant question about gold is, I've always believed that it was named after my favorite Spandau Ballet song.
I wish. Well, I imagine that was on Gareth's mind deep down when he came up with it, but it may well have been, but it does stand for something like genetic optimization for ligand docking.
Yeah.
Which is much more mundane and boring. It'd be much better if it's Spandau Ballet, I think.
Well, I have told people this during many of our training sessions, so hopefully it catches on. And
it pretty much finishes on it does fit in with the dates. Of that particular
exactly.
Problem. Yeah,
it always dates me when I say it out loud. And the old people say Spandau what now?
Yeah, indeed. There you go.
There was one other question. I guess we wanted to put a plug in. Are you all still looking for a chief executive officer or executive director?
We are. I believe the advert is out, and I think it's still open. I assume it will still be open by the time this podcast goes live, but the trustees and the executive are busy beavering over looking for the right candidate, someone with a good business head, but hopefully also a knowledge of charities and also a scientific background. So, no, we're not asking too much, are we?
Just somebody who's good in everything.
Yeah,
exactly.
Yeah,
That's very
pretty
reasonable.
much.
And then we got two more questions for you if you have the time.
That's fine.
The one question is, so you mentioned you went up with your colleague, I think you said his name was Nigel? And then
Nigel Pitchford, yes.
Nigel cashed in, right? Nigel went a different path than you and said, oh, gosh, I can take my quantitative background and I can probably earn gobs and gobs of cash. But then you also mentioned that he's now a member of the board.
He is a trustee, yeah.
How did that happen? Do we know about this? I'm sure you do.
Someone at CCDC, and I couldn't possibly mention who, suggested that a chap called Nigel Pitchford that he happened to know from years before might be a good person to think about as a trustee. we were looking for someone who with expert in financially savvy trustee, because you need a really broad portfolio of people to be serious. And so I thought, Nigel worked here, so he is a bit unique in the sense that he's actually got knowledge of the first-hand knowledge of the organization. He's also worked in finance and gone and done, investment banking. And so, but also in a scientific belt. I mean, Nigel's experience, his first company, I think, was a company called 3i. I don't think they exist anymore, but they were massive investment, but specifically in high science type projects. That's where their area of interest was. So, he came from that background, but also with the knowledge of CCDC, which is why he seemed like an ideal fit. And he decided he did have the time, and so now he's on our board.
Nice.
So we have a really broad portfolio of trustees. We have from academics across the board to someone who's much more industrially focused, people who are in business, but the chemistry business, and so on and so forth. So we have somebody from AstraZeneca, for example, and a good cross section of trustees to provide with their insight and knowledge.
Yep, nice. That's great. And then the one last question, we've been asking this. So I was kicked out of the podcast for one episode. And I can't remember why Chris kicked me out, but he invited me back. And the person who took my place, Alain Deschênes, he's our vice president of vice presidency things. And Alain came up with this dilemma, right? So at the end of the podcast, we ask you, if you weren't doing what you're doing now, right, what would you be doing?
Goodness me, that is a good question. So I guess it changes over time. If you'd asked me that 30 years ago, I probably would have said a chef.
Okay. No, I
love cooking. I love cooking. So
I totally get it.
And it's chefing. Being a chef's a chemist, right? At the end of the day. So I think that would have been the thing. If you ask me now what it would be, if I was to sort of go and do something different tomorrow, that would probably be a different thing. And just because of my own personal experiences, I think it would still be charitable. It would still be working in a charity. It's just because of my middle son, I'd probably go and work, for something like a charity advocating rights for disabled people or something along those lines. And just purely from a personal perspective, that's probably where I'd go now. But probably the alternative career path would have been crazy late nights cooking.
Yeah, well, the thing is that the thing about the life of a chef, it is harder than a lot of people think, and it's like,
it's a terribly hard life. Yeah,
hard life. And I enjoy cooking myself, and I'll cook for neighbors, and I'll experiment with cuisines, and they'll say, "Why don't you open a restaurant?" It's like, no, because I like cooking.
Yeah.
Once you open a restaurant, it's not about the cooking; it's about a whole bunch of other stuff.
Delivery, basically.
Yeah, exactly. Yeah. But I think even with being a chef, being a scientist, providing software for people, and also wanting to work in a charitable organization, I see the common theme is you like to help people. You like to make people happy.
I think the best thing about any career probably, but certainly my career at CCDC has been the people. I've always had the opportunity to work with brilliant people. It's lucky I've worked with brilliant people because, you know, they cover up for my inadequacies, I think. You know, I think, you know, I've had the opportunity to work with some really great people in the organization.
Yeah.
And I think, yeah, those sort of relationships and working with people in that way is what actually really floats, you know, that does float your boat.
Yeah.
And most of the time it all works fine.
Such a nice ending.
Well, I mean, you've been there 30 years. That's a testament to, you know, the work environment, I guess, at CCDC, that you can stay there that long. And, you know, they say people don't quit jobs, they quit bosses.
Well, there is that, yes, yeah. But my bosses seem to have quit me.
I guess it's one of the strategy, right? You just have to outlast them.
No, I'm teasing, but anyway, no, I think, I say, and I've seen it from both sides because I was a deputy director for a period, so I was the second in charge at CCDC, and it is, you know, I don't think people necessarily at the coalface always understand just how tough that is as well, because you're faced with a whole load of different opinions and you've got to deal with all of it, and you're faced with a whole load of different drivers and different decisions and different tensions and the like, and I have utter sympathy for anyone dealing with all of that, because sometimes you're in Zugzwang, as they say in chess. You know, you cannot make a right move. There is no good move that you can make. And so you know, I think, I have the greatest respect for people who actually take on the executive roles in organizations.
Mm-hmm.
So. Okay.
All right. Well, look, Jason, it's been an excellent conversation. Thank you very much. I'm sure we could probably even talk longer.
We probably could, yeah. But
we probably could, and you know, but it doesn't mean you can't be a guest on yet another day. You know, I'm sure different
Who
things.
knows?
Well, I think the things that come up. CCDC's still evolving. You know, Mo's still evolving. Our field is still evolving. Right? We didn't really touch on AI too much, but I think, you know, we'll see what happens. We'll see what happens in a few years with all that.
Who knows? That is always an area of interest. That and the other one, which is coming, perhaps not in my career, but maybe in people who are sort of 10 years younger than me, they're going to have to start thinking about in more detail about quantum computing. It seems very, very soon, and how that is going to impact the area. I think is very interesting indeed. Mm-hmm. I still can't decide whether it works or not. So we
yeah, we shall see. We shall see. I mean, it's a little like fusion. You know, it's going to be here in 10 years. They've been saying that for 50 years.
Yeah. But we shall see. Yeah,
we shall see. Okay, look. Thank you again, Jason, very much.
Thank you very much, Jason.
Have a good rest of the day, and thanks to our listeners. Everyone take care and keep thinking science.
It's been a pleasure. Thanks, guys.
Right. Cheers.
See you next week.
Thanks for listening to this week's episode of Under the Surface. Don't forget to subscribe to our podcast on Apple Podcasts, Spotify, and other platforms so you don't miss an upcoming episode. Enjoying our podcast? Please rate and review us on Apple Podcasts and Spotify. Have topics or speaker suggestions for future episodes? Send an email to podcast@chemcomp.com. That's podcast@chemcomp.com. Until then, keep exploring, keep learning, and keep loving the science. Signing off.